we can use this equation for the combustion of octane. Octane reacts with oxygen to form carbon dioxide and water as being representative of fossil fuel combustion reactions. There's just so many different compounds that are present in fossil fuels. There's no way you could look at all of them or know what was present in the gasoline in Minnesota versus the gasoline in Kansas. So we're just going to use this to represent fossil fuel. So what this tells us is that for every 2 molecules of octane that react, I get 16 molecules of CO2. Or I can say that I get 16 moles of CO2 for every 2 moles. Because I can look at it as individual molecules. I could look at it as 2 dozen to make 16 dozen. But this is chemistry, so we're going to use the chemist's dozen mole. 2 moles of octane make 16 moles of CO2. These coefficients tell us the relative amounts of moles of the substances, not their masses. Okay? Get that small enough. The amount of substances used and made in the reaction, they are all related to each other. The reactants are related to each other, the products are related to the reactants, etc. And this is because of the law of conservation of mass. We balance the equations by balancing the atoms. And so we can use the chemical equation to study amounts of substances in chemical reactions. And the study of that numerical relationship is called stoichiometry. Stoichiometry is one of the big deals in chemistry. It's important to understand stoichiometry. If you can't solve one of those combustion analysis empirical formula problems, you can still get an A in this class. You'll be fine, right? If you can't do stoichiometry, you're probably not going to pass because this is going to show up all over the place. So stoichiometry is important. So we're going to talk about pizza. I hope everybody had lunch. It's kind of odd. My night class is at 5, and so it's like I hope everybody had dinner. So we could look at a recipe as being a lot like a chemical equation. We're looking at the reactants, the ingredients, and what is formed or produced. So 1 crust, 5 ounces of tomato sauce, and 2 cups will give you 1 basic cheese pizza, right? And we can look at this as mathematical ratios. There's 1 crust for every 5 ounces of sauce, for every 2 cups of cheese, for every 1 pizza. And so we can use those ratios to calculate how many pizzas we could make from 10 cups of cheese. How many pizzas could we make? It's not a trick question. 5, thank you. Right? You're like, that's too easy. I don't dare say anything because she's going to tell me I'm wrong. No, it's just 5, right? Well, how do we do that? We understand things like recipes. We know how that works. You need 2 cups of cheese for every pizza. If you have 10 cups of cheese, you have enough for 5 pizzas, right? So we can do this with everyday objects. When we go to moles of oxygen, we're like, and we freak out. So let's learn how to write this down in an equation so that we can do the same thing when we freak out about the oxygen. So this is just dimensional analysis. I'm taking 10 cups of cheese and I'm converting that to pizzas. The great thing here is you can relate any 2 of these things. So it's always just 1 step. So 10 cups of cheese. I have one arrow, I have one conversion factor. I'm going to have pizzas on top, and I'm going to have cups of cheese on the bottom, so the cups of cheese cancel out. The relationship between pizzas and cups of cheese comes from this equation. There are 2 cups of cheese for every 1 pizza. For every 1 pizza, I need 2 cups of cheese. And so we end up with 5 pizzas, which is the answer you came up with in your head. Do you see how this is dimensional analysis, like when we were doing inches and centimeters and stuff? We'll have a path. We're starting with one thing. We're trying to find something else. Now, the path is going to get a little bit longer, but right now it's just one step. So we can use the ratios of the coefficients in a chemical equation as conversion factors between moles of reactants or products. And we can relate any 2 reactants or products. You can have 2 reactants or 2 products, 1 product and 1 reactant, any combination. So if we burn 22 moles of C8H18, how many moles of CO2 form? Well, 22 moles of C8H18, and we're trying to figure out moles of CO2. I guess if we highlight it like I've done the other problems, that's what we're given, and that's what we're trying to find. The relationship between moles is right in the chemical equation. 22 moles of C8H18. 1 factor, moles of CO2 on top, moles of C8H18 on the bottom. Yes, it gets tedious writing all the chemical formulas. It's important though, because otherwise you get the problem wrong and you have to do it over again, and that's tedious. And you do that too much, and you take the class over again. Super, super tedious, right? Nobody wants that. Just write the formulas. So moles of CO2, moles of C8H18, these come from here. I just thought of something. This might be fun. So there's 2 moles of C8H18 for every 16 moles of CO2. So I'm literally just taking that number. 2 is for the C8H18. So I'm going to put that down there. And the 16 goes up there. It's just as simple as the pizzas, except we're talking about oxane. That isn't even a thing, octane, and CO2. Could you simplify that? Sure. Do you need to? No. So my feeling is just leave it alone. So 22 times 16 divided by 2, 176 moles of CO2. Checking sig figs, my starting number had 3 sig figs. These integers in the balanced chemical equation are all exact numbers, because we will get exactly 16 carbon dioxide molecules from 2 octane molecules, because there are 16 carbons in there. It's individual pieces. So this is 1-to-1. So what that means for sig figs is these mole ratios, you use them, they're not going to affect the sig figs. Okay? So here we've got 3 sig figs. Of course, we don't measure things in moles because, well, you can't. We measure things in grams a lot. But we've learned how to convert grams to moles and moles to grams, right? So we can combine, using molar masses with what we just learned about that mole ratio from the equation. And this gets us what could be referred to as a general conceptual plan for stoichiometry. You're starting with the mass of compound A. You convert that to A in moles. You convert that to amount of B in moles. And then you convert the moles of B to mass of B. So in a shorter form, this is grams to moles to grams. So that is the path that you start with for any stoichiometry problem. Then you look at your problem and you might have to modify an end, but there's going to be mole to mole in the middle. A TV show, Malcolm in the Middle, right? Moles in the middle. So grams to moles to grams. And you know you're getting it when you wake up in the middle of the night mumbling grams to moles to grams, right? So that's your goal. Apologize to any roommates in advance. Okay, let's do an example of this. According to the U.S. Department of Energy, the world burns 3.3 times 10 to the 10th barrels of petroleum in 2013, which is the equivalent of approximately 3.7 times 10 to the 15 grams of gasoline. Calculate the mass of CO2 emitted into the atmosphere using the combustion of octane as the representative equation. Well, let's identify what we were given. It usually involves numbers. Here we've got this many barrels of petroleum. Haven't used barrels yet. And this many grams of gasoline. And they're asking us for mass of CO2. Okay? Well, this first one, the barrels of petroleum, we don't actually need to use that because they've already interpreted or converted that into approximately this much gasoline. And we're going to use octane to represent the gasoline. So I like to use the balanced chemical equation to take those numbers and organize them. And so I've got gasoline, which we're using for C8H18. And so I'm going to write 3.7 times 10 to the 5th grams of that guy. And then what am I trying to find? The mass of CO2. So under CO2, I'm going to put a question mark. What unit would be easy for mass? Probably the same unit that the other thing was, right? So grams. So my path is going to be this many grams of C8H18. I want to end up with grams of CO2. What goes in the middle? It is 10 to the 15. Yes, I did that yesterday. Thank you. Thank you very much. It is 10 to 15. That would be a gross underestimation. So I've got grams at the ends, and what goes in the middle? Moles. I want grams to moles to moles to grams. So I can convert grams of octane to moles of octane. What I'm doing there is I am changing the unit but not the compound. Changing one thing at a time. And then I'm going to go from moles of octane to moles of my product, which is CO2. Here I'm going from one compound to a different compound. And I can do that because the chemical reaction gives me the relationships. And then moles of CO2 to grams of CO2 is going to use the molar mass of CO2. Any questions? So there's our path, grams to moles to moles to grams. We'll write it down with 3 fractions, stick the units in, then put the numbers in, and it's all good. So 3.7 times 10 to the 15th. Get it right this time. C8H18. So I'm going to have three fractions. The first one is going to have moles of octane. Right? There's Dora talking about the path she's going to follow. And the second one is going to be moles of CO2. And the last one is going to be grams of CO2. Grams octane, moles octane, moles CO2, grams CO2. Grams octane, moles octane, moles CO2, grams CO2. Grams to moles, grams. Much faster. Any questions about that? We're going to do the same thing we did with dimensional analysis, because this is dimensional analysis. This unit comes down here, so it cancels out. And put moles down here, so it cancels out. And we put moles CO2 down there, so it cancels out. Now that we have the units in place, the units are going to tell us where to put the numbers, much less thinking. I like to start in the middle because it's easy. Moles of CO2 and moles of C8H18. Where do I get those numbers? From the equation. It's 2 moles of octane, so I'm going to write 2 moles of octane, 16 moles of CO2. 16 moles of CO2. That one's easy. The beginning and the end, we're going to have molar masses, and most of the time we'll have to calculate those, and so that's why you got so much practice on that last week. So we need the molar mass of octane, and I highly encourage you to write down what I'm going to write down. It's just a very sketchy form of showing your work. I've got 8 carbons, and the mass of carbon is 12.01, plus 18 hydrogens times 1.008 equals. So calculator says 114.224 grams is the mass of 1 mole of octane. That probably should only have 4 significant figures, but we're going to use it in a calculation. Let's not round it. We're just going to use the whole thing. And if we think ahead about sig figs, how many did we start with? 2. Just 2. Because this is an estimate based on another kind of an estimate and another estimate. So this is, just 2 sig figs and then a whole mess of zeros. So our answer is going to have 2 sig figs. This isn't going to impact it at all. We also need the molar mass for carbon dioxide. So I have 1 carbon and 2 oxygens, and that's going to give me 44.01 grams. Over here, grams is in the top, so I put grams and 44.01 together. No remembering, should I multiply, should I divide, just put it with the unit. So now we just do the whole thing in one swoop on the calculator. 3.7 EE15 divided by 114.224 times 16 divided by 2 times 44.01 equals 1.140 times 10 to the 16 grams. I should have 2 sig figs. I'm going to write down 2 extras, and then I'm going to report the rounded answer. Any questions? So we just calculated that Petroleum combustion produces 1.1 times 10 to the 16th grams of CO2 per year. They estimate that volcanoes produce about 2 times 10 to the 14th grams of CO2 per year. That's a lot of CO2, but it's smaller, right? It's hard just looking at those numbers to see the magnitude of the difference. So let's find what times. How do you say that? By what factor is petroleum combustion bigger? We're going to divide the big one by the small one. 1.1 times 10 to the 16th grams divided by 2 times 10 to the 14 grams. The units gram cancel out, and we get 55. With this being 1 sig fig, it should round to 60, but you know. So petroleum combustion accounts or produces 55 times more CO2 than the volcanoes. Are the volcanoes our problem? No, it's us. Petroleum combustion is the big contributor. Any questions? Let's do another example. Magnesium hydroxide, the active ingredient in milk of magnesia, neutralizes stomach acid, which is primarily HCl, hydrochloric acid, according to this reaction. Milk of magnesia sounds friendly, doesn't it? It's magnesium hydroxide. It's a chemical. Stomach acid sounds better than hydrochloric acid. We all have hydrochloric acid in our stomach, which is good because if we didn't, we couldn't digest our food. I just have this thing about people who freak out about chemicals, because the air that we're breathing is a chemical. The water that you drink is a chemical, right? It's just some of them are more dangerous than others. Okay, so that's all nice. What mass of HCl in grams is neutralized by a dose of milk of magnesia containing 3.26 grams of hydroxide? So I'm given 3.26 grams of hydroxide, and this is telling me to find mass of HCl in grams. So if you have difficulty with story problems, with word problems, go through and highlight or circle or underline anything with a number, because that might very well be important, and then look for a question word. What? What mass? That tells me what I'm looking for. So I'm starting with grams of Mg OH2. I want to end up with grams of HCl. How do I get there? Moles. There needs to be moles in the middle. So moles of magnesium hydroxide to moles of HCl to grams of HCl. Grams to moles to moles to grams. I'm going to take my number, my mass of magnesium hydroxide, and write it under the formula in the equation. 3.26 grams of that. And what am I looking for? Looking for HCl in grams. So there I have what I'm looking for and what I'm starting with. So now the process is just like the previous one. We're going to write this out. We have 3 arrows. There's 3 conversion factors. 3.26 grams of magnesium hydroxide. I'm going to convert that to moles of magnesium hydroxide. To moles of HCl to grams of HCl. Grams to moles to moles to grams. Get all the units written in there first. Those are going to cancel. Those are going to cancel. Those are going to cancel, right? Well, I've got my moles in the middle, and that's my easy one. How many moles of HCl from the equation? 2. 2 moles of HCl, and how many moles of magnesium hydroxide? 1. Then I need molar masses of both of those compounds. 1. I don't know why I can't remember this one anymore. Yeah, it is 3-1. So magnesium, there's one of those, 24.31. How many oxygens? 2, right? I've got parentheses around the OH, and it tells me on the outside there's 2 of them. So that's 2 O's and 2 H's. So 2 oxygens and 2 hydrogens. $58.326. So for the magnesium hydroxide, the unit gram is on the bottom, and that's where the number goes. Then I need the molar mass of HCl, which is 1 hydrogen and 1 chlorine. So 36.458 grams. Here grams is in the numerator. That's where I put my number. .326 divided by 58.326 times 2 times 36.458. How many sig figs should my answer have? 3. The number I started with had 3 sig figs. My molar masses had 4. That's exact. None of those are going to matter. So I should end up with 3. Here's my 3, 4.07, next 2 digits. And then rounding that, I'm going to get 4.08 grams. Any questions? .08. One more example. A component of acid rain is nitric acid, which forms when NO2, a pollutant, reacts with oxygen and water according to this simplified equation. The generation of the electricity used by a medium-sized home produces about 16 kilograms of NO2 per year. Assuming that there's adequate O2 and H2O, what mass of HNO3 in kilograms can form from this amount of NO2 pollutant? There's a lot of words. Read the words, and then go looking for numbers. So I see a 16 in there. 16 kilograms of NO2. And then, where's the question word? The question word is what? Oh, that's not what I wanted to do. What? Right? What mass? So I'm looking for mass of HNO3 in kilograms. So HNO3 is what I'm finding. And NO2 is what I'm starting with. So I have 16 kilograms. of NO2, and I want to know how many kilograms of HNO3. Okay? Well, what's the typical path for stoichiometry? Let's all say it together. Grams to moles to moles to grams. So I'm going to write that down up here. Grams to moles to grams. But they didn't give me grams. They gave me kilograms. Well, could I convert kilograms into grams? Sure I could. So I'm going to put kilograms to grams in the beginning. Yep. And then at the end, I'm getting grams, and they want kilograms again. Well, can I convert back to kilograms? Sure I can. What we'll see is that those conversion factors cancel out, and there are faster ways that you can do this, and if you understand those ways, that's fine. But if you don't, just do it the long, slow, and steady way, and you get the right answer. And that's a good thing. Okay, so we're starting with 16 kilograms of NO2. And the path says we're going to convert that to grams of NO2. And then we're going to convert grams of NO2 to moles of NO2. And then to moles of HNO3, which is nitric acid. From moles of nitric acid to grams of nitric acid to kilograms of nitric acid. Yes, it's long, right? It's just, well, there's got to be a faster, simpler way. Well, not really. I mean, there's some little shortcuts you could take. If you were doing this calculation all the time, you'd program Excel to do it for you. We don't want to memorize a whole bunch of different ways to solve problems. Here, we've got one method, dimensional analysis, and we can use it on all of the stoichiometry problems. Okay? So please use it. So, with the units. Kilograms of NO2, grams of NO2, moles of NO2, moles of HNO3, grams of HNO3. I like to start in the middle because it's easy. I've got HNO3, this guy, and there's a 4. So I'm going to write 4 in front of its formula. And over here for NO2, there's also a 4. So I'm going to write 4 there. Here at the beginning, I'm converting kilograms to grams. And kilo represents times 10 to the what? Third. Let's try that again. Times 10 to the 3, positive 3. So I have the abbreviation down here. I'm going to write what it means on the other side. 1 times 10 to the 3rd grams is equal to 1 kilogram. Over here, I also have a factor relating kilograms and grams. Over here, kilograms is in the numerator, and so I'm going to write what it means in the denominator. And I get 1 kilogram is 1 times 10 to the 3rd grams. So those two cancel out, don't they? So if you don't want to punch those through on your calculator, you could just say, oh, well, the numbers are going to cancel there too. I don't have to type all that. And then we need molar masses again. We end up calculating molar masses over and over and over again. So nitrogen is 14.01 and 2 oxygens is 16. .01 grams. So 46.01 grams for 1 mole of NO2. And then I've got HNO3, so that's a hydrogen. It's a hydrogen and a nitrogen and 3 oxygens. .018. So here's where I use the molar mass of nitric acid. I put the number with grams. And sometimes it gets a little squishy. So I've got 16 divided by 46.01 times 4 divided by 4, as long as we're canceling things out. We can cancel those out too, huh? Times 63.018 equals 21.9. How many sig figs should this answer have? Just 2, because 16 is just 2. So the unit here is kilograms, because that's the unit that didn't cancel out. So we're going to say 22 kilograms of nitric acid. That's the mass of nitric acid from one house using electricity in a year. It's a lot. Any questions?